Hello, students, problem solvers. I'm going to be doing this for the PowerPoints for the next 4 lessons at least. So the next lesson after sets, which was before break, is functions. And so we'll do this and then I'll go through the ICE sheets. So function is something that you're familiar with and you probably thought about vertical line tests and that kind of thing. But a function can be defined on any set to another set. Usually we're thinking about R and R as the two sets, but any set to any other set. But each set in the first part, the domain, is what we'll call that, has a unique element f of a in the target set or the codomain. So I'd never send one element to 2 different places. That wouldn't be a function. F of a, the output, that's called the image or the value under f. And then the arrow indicates that we're going from set A to set B. The set A we'll call the domain. Set B we might call the target, or we'll call it the codomain. We're not going to call it the range. The range is the stuff you actually hit in the target space or the codomains. The image or range is, think of applying F to a whole set, so all the outputs possible from the domain. So you might hit everything, you might not. It's often the case that the image is a proper subset of the target. So here's an example. The little small circle on the right is the image or range, but the target space is the whole bigger set. But everything in the domain goes somewhere, and then the places it goes is the image. And notice that the top 2 dots on the domain go to the same place. That's possible as well. I don't have a dot having 2 arrows come off of it on the left side. So given a specific function, the function determines the output, right? So the output is called the dependent variable, the input A, that's called the independent variable. Which of these are functions? So the first one says if you have as your input a set of years between 93 and 2005, B is natural numbers, and then you should take a year and you should output the number of North Atlantic tropical storms and hurricanes in that year, which is going to be a natural number. Let's talk about that one first. So each year has an output because you input a year and you just maybe get 0, but you get out the number of storms that happened. And 2 different years can have the same number of storms, but every year has a unique number of storms plus hurricanes. So that makes sense. Go to the next one. If A is the set of divisions in the NBA and B is the set of teams, F of A is the teams in division A. So you input a division and you output, let me repeat that, you input the divisions and then you output the teams in the division. So let's think about this for a minute. A division can have multiple teams, so if you input one division you can output several teams, which means this is not a function, right? So if you have one input giving you multiple outputs, that would not be defined as a function. These are relations. So think of ordered pairs. So like in the first one, 0 goes to 1, 1 goes to -2, and so on. And which of these fit the definition of function? If you look at this first blue dot, 0, 1, 2, and 3 are the domain values. They each have somewhere to go, and they all go to places in the target space. So that looks good. That's a function. The second blue dot, this is not good with the 5 listed because 1 is going to 2 places. 1 is going to -2, but 1 is also going to 1. And then if you look at the third one, that is not a function because it's, well, at least it's not a function on A because we didn't send 2 anywhere. So its domain is not A. So that would not be a function on A. So when we talk about well-defined, a function can be specified by different rules and different subsets of A, but to know if f is actually a function, you need to check that the rules don't overlap. And where you've seen this before in calculus or in pre-calculus is piecewise functions. At the endpoints, you couldn't have the same x value having 2 different definitions. If everything works out okay, we call that function well-defined. 2 functions, f and g, are said to agree if they have the same domains, the same targets, and for every element of x, they're equal. The most common example of this I use in calculus is that x and x squared over x are not the same function. One has a whole, one does not. The vertical line test is how we check that an xy graph, if that's a function, the domain hits the graph precisely once. And if you hit the graph either not at all or more than once, then that doesn't work. So that's why usually when we're thinking about the vertical line test and we're trying to figure out the domain of a function, we're trying to cut it down to where you actually do hit the graph with those vertical lines. So here are some functions. They're not all continuous, they're not all differentiable, but they all are functions. And notice that the first two do not, well, actually none of them hit the entire target space, the y-axis. These are not functions simply because none of them pass the vertical line test. What can I do with functions? Well, I can add them. That would be a function. I can multiply them. Difference and quotient also work, but just make sure you don't divide by 0. Composition is always a tricky one. Notice that the B's, F goes from A to B, G goes from B to C. And so they don't have the same domain. F's output needs to be G's input. You can force it, then you get a new function from A to C. B is kind of the stepping stone in between, and we call that G of F of X. F of G of X is another function, but you'd have to flip all the domains and target spaces around. So here's an example. X goes to, think of this like an assembly line. X goes to F of X, which goes to G of F of X. So F goes from X to Y, G goes from Y to Z, and Y is kind of just a placeholder. Once you get G circle F, you kind of skip over Y, but it still happens kind of in the middle. Composition is not commutative. You can't flip it the other way around, but it is associative. The identity function is kind of important because we need it for inverses. So identity function from a set to itself is just that you don't do anything. You input what your input is your output. Nothing gets changed. So when I compose two things, if I get the identity function, then that's called the inverse. Notice that F and G have domain and range that are flipped. And the most important here with notation, we use f to the minus 1 for inverse. That is not 1 over f. It's not the reciprocal of f. So x cubed has inverse x cubed has the inverse cube root of x. X squared has no inverse on its whole domain. You have to chop it down to 1/2 of it. So square root x is technically not the inverse of x squared. Graphically, this is x cubed and cube root of x. Because they compose to y equals x, their graphs look like reflections over y equals x. So you can see that the red and blue are reflections over the green line. To have an inverse, we need to be an injective function, or usually I'm going to call this a one-to-one function. The simpler way to remember this is that different things should go different places. So you shouldn't have two guys going to the same place. But in proofs, you're usually going to want to start with equal outputs and then get equal inputs. That's the contrapositive of what I just said. But you don't really want negative statements when you're trying to do a proof. So intuitively, different things go to different places. Proof-wise, if they went to the same place, then they were the same thing. So in a one-to-one function, we call that an injection. This is also the horizontal line test. So for each element in the codomain, there's one element in the domain that maps to it. Sorry about that, guys. So an injective function on the left, it's not onto, but it is injective. The second one is not because two things went to the same place. For these, I want the horizontal line test, so the middle graph would be injective. A surjection, I'm going to call this an onto function, means that you hit everything in the target space. So it says for all B in the target space, there is an A in the domain that it was mapped by F to that B. So the range equals the codomain. We call that a surjection. I'm mostly going to use one-to-one and onto. So you have to have at least one element in the domain hitting that guy. So the last one is surjective. It is not injective. Two things go to the same place, but it hits everything on the right side, and then the other one is not surjective. For this, which is surjective, that would be the far left one because you hit all reals, and then the second and third graphs, you don't hit every y value. If you're one-to-one and onto, we call that bijective, or this is confusing, one-to-one correspondence. That word correspondence implies that it's also onto or surjective. So we want both properties. One-to-one correspondence implies one-to-one and onto, even though they don't use the word onto. So we call that a bijection. I might say that sometimes. I like bijection better than one-to-one correspondence. So another way to say that is for each element in the codomain, there's exactly one element in the domain mapping to it. So this is a nice graph where everything, one guy on the left goes to one guy on the right, and everything on the right gets hit. Sometimes I use the example of picket dates. So in this case, if it's the guys asked the girls, every girl was asked, and no girl was asked by two guys. Whatever it takes to get you there. If you have a bijective function, so you have this one-to-one correspondence, that is a theorem here that a function has an inverse if and only if the function is bijective. You've probably heard that it's injective, so if it passes the horizontal line test as an inverse, that theorem seems to contradict this one. That theorem is about tweaking the domain to make it work. If you've got a set or domain and codomain, then this is the theorem. Other idea about an image of a set, we already talked about this earlier. If you have a subset of the domain, you can just take f of a set by just saying, hey, that set is all the outputs from there. So here, this is C, the green stuff is C, and then f of C is just the places they went to together as a set. So you're mapping a set to a set. It's basically just doing a bunch of function outputs at once. The inverse image of a set, or I will call this often the pullback, is not really what I mean by an inverse function, because you don't have to be an inverse to do this. So it's not great notation, but it's what we use. So you have a subset of the range, and you want to go back to the domain, so that's why I call it a pullback. You take the elements that went there. So f inverse of a set doesn't mean the function's invertible. We're just asking what elements went there. So here's D on the right, and then f inverse of D are the green stuff on the left that went to D. And notice this function's not invertible, but we still use this notation.